So section 5.4 wants us to start to identify features in the graphs of essentially fractions. And sections 5.4 and 5.5, I could have made it into one insanely long section, but I made it into two moderately long sections that might feel insanely long. So I'm just going to jump into the problems. And the idea is section 5.4 is to prepare us for section 5.5. Section 5.4, we're going to do algebra to find features of the graphs of fractions. And section 5.5, we're actually going to graph fractions. And I know this section 5.4 is going to take at least 2 videos, so let me just start. So the first 16 problems ask us to do multiple parts. There's a part A and a part B. Find the domain of the fraction and express your answers in words, and then find the equation of the vertical asymptote. Finding the domain of fractions is something you do in most algebra courses before this. So to do problem 2, part A, to find the domain of this fraction, the algebra you're going to do is you're going to ignore the numerator. You're going to solve the denominator equal to 0. That's the algebra that's going to be needed. And then I'm going to write my answer in the requested form. And in problem 2a, I'm supposed to find the domain and express my answer in words. So I'm going to express my answers in words. The algebra to find the domain of a fraction is just to ignore the numerator and set the denominator equal to 0. The algebra that I did to set the denominator equal to 0 gives me the answer x equal to -3 because I subtracted 6 and divided by 2. To write my answer in words, if I said the domain is x equal to -3, I would be wrong because x equal to -3 is actually the only number that's not in the domain. It's the only number I can plug in for x into this fraction and get undefined. So when I go to write my domain for this fraction, so I'll say the domain of the fraction f of x equals 3x minus 12 over 2x plus 6 is every number, maybe every real number, except or excluding x equal -3. And that would tell somebody that reads mathematics that if you plug -3 in for x, you're going to get undefined as an answer. But if you plug any number other than -3 in for x, you'll get something that's defined. It may be a fraction, it may not be a fraction, but it won't be undefined. That's the end of part A. For part B, find the equation of the vertical asymptote. Any number that's outside the domain of a fraction graphically either produces a whole or a vertical asymptote. So every number that is not in the domain of a fraction, in this case the number -3, on the graph of that fraction either produces a whole or a vertical asymptote. Wholes are tricky to see on my calculator, and kind of for that reason we're not going to cover them in our class. I'll show you in a second what I mean by a whole, but we don't have to worry about those coming up for our class. So for our class, for every number that's not in the domain of a fraction, it's going to produce a vertical asymptote. When I go to answer part B to find the equation of the vertical asymptote, the algebra that I do to find the numbers to exclude from the domain actually gives me the answer to part B, the equation of the vertical asymptote. So let me do a little sidebar and talk about holes and vertical asymptotes real quickly. I'm done with part 2a and 2b. There isn't anything more to do. I don't think I want to talk any more about these functions because these functions don't have holes, and the vertical they do have vertical asymptotes. So let me just do something that's maybe a waste of your time. And if you fast forward to me doing problem 4, it's not going to hurt my feelings. For that matter, if you just do problem 1, just in case you haven't done it yet, fast forward to me doing problem 4, you're not going to really lose out here. So I'm going to make up two fractions. Here's the fraction f of x equals x plus 3 over x plus 3. And how about the fraction x minus 4 over x plus 3? To find the domain for each one of these, you're going to ignore the numerator and set the denominator equal to 0. The computation to find the domain in the first fraction is exactly the same as the computation to find the domain in the second fraction, because to find the domain of a fraction, you ignore the numerator, you set the denominator equal to 0. For both of these, the domain is all real numbers except x equal to negative 3. I wrote a really cheapy answer because I'm not doing this for homework. In this function, on the graph, there's going to be a hole above x equal to negative 3. And in this fraction, there's going to be a vertical asymptote that goes through x equal negative 3. Let me graph this fraction and show you what I mean about the hole. I'm not sure how well we're going to see the hole, but I'm going to go y equals clear x plus 3 divided by x plus 3. Let me try zoom standard after I get that function in right. And you can't see above x equal to negative 3 a hole. Let me try to fix that by going zoom. What zoom do I need to do? Maybe zoom integer might do it. Oh, that's no good. Oh, you can actually see the hole now. Ugh. When I hit zoom integer, I don't really know this graphing on my calculator so much, but when I hit zoom integer and hit graph, what it did is it totally messed up the window, but it showed the hole. And this right there, that hole is at x equal to negative 3, and it's not something called a vertical asymptote. There's actually a hole in the graph at x equal to negative 3. I'm going to not go dig my hole any deeper than I've just dug it on this because I'm not very talented with holes on my graphing calculator. So there's a break in the graph that the graph in some sense is just, if you filled in that hole, the graph would be connected and it'd be a continuous graph. Whereas this function right here, I say has a vertical asymptote at x equal to negative 3, and this is what we're responsible for. So let me just graph this going back to a zoom standard. And what happens at x equal to negative 3 is there's a break in the graph. As opposed to being a hole that you can fill in to connect two halves of the graph, there's a physical break at x equal to negative 3. Unfortunately, if I want to graph x equal negative 3 on my calculator, it's virtually impossible to graph vertical asymptotes because my equations need to be solved for y that I graph, and this equation doesn't have a y in it. So if I want to graph a vertical asymptote on my calculator, I'm going to do something to cheat. So I'm going to cheat to graph something that looks like a vertical asymptote, but really isn't. So this graph has a vertical asymptote at x equal to negative 3, which means if I draw a vertical line through x equal to negative 3, it's going to split the graph into two halves. The right half of the graph will get microscopically close to that vertical line that goes through x equal to negative 3, but it won't touch nor cross it. Similarly, the left half will do that. To cheat to get a vertical asymptote, just take the factor that produced the vertical asymptote and multiply it by 1,000 and put that in your y2. So if I go to y2 and take the factor that gave me the vertical asymptote of x equal to negative 3, which is x plus 3, multiply that by 1,000, it's going to graph something that looks like the vertical asymptote through x equal to negative 3. And what happens is, the lower the graph goes on the right-hand side, the closer it gets to this line, but it doesn't cross it or touch it. Similarly, the higher the graph goes on this side, the closer it gets to this line, but it doesn't cross nor touch it. If in my window I make the y's go higher and lower, you'll start to see what happens with this vertical asymptote. The higher the graph gets and the lower the graph gets, the closer it gets to this line, to the point where the graph gets so close to the line that my calculator can't distinguish the graphs from each other. So for our purposes, any value that makes the fraction undefined, or any number that's not in the domain of a fraction, is going to create a vertical asymptote. The way you get wholes is if the number that makes the fraction undefined, or that's not part of the domain, can be canceled out. The factor of x plus 3 would cancel out of this, which means it cancels out the vertical asymptote and turns it into a whole. That's even more than I wanted to say, and I don't even know if it was the best lecture I've ever done on wholes and vertical asymptotes. But for our purposes, we're not responsible for wholes. Any number that we find that's outside the domain of the fraction is going to give us a vertical asymptote. So as I go to do questions 3 and 4, part A, find the domain, express my answer in words. Part B, write my equation of the vertical asymptote. They're going to be very tied together. So for 4A, to find the domain of the fraction, I'm going to ignore the 3x minus 18, and I'm going to solve x squared plus 5x minus 6 equals to 0. When I solve this, I'm going to solve by factoring because of the square. That factors into x plus 6 times x minus 1. I'm going to set x plus 6 equal to 0 and x minus 1 equal to 0. When I set x plus 6 equal to 0, I get x equal to negative 6. When I set x minus 1 equal to 0, I get x equal to 1. Those are going to be the equations of my vertical asymptotes. And those are part of my answer to the domain of the fraction, but they aren't my answer. For 4a, the answer, if I want to write a very wordy answer, I can say the domain of the fraction f of x equals 3x minus 18 over x squared plus 5x minus 6 is all real numbers except negative 6 and positive 1. When I move on to 4b, to find the vertical asymptotes, our vertical asymptotes are going to be the equations that I derived when I'm solving for the numbers to exclude from the domain. So it's going to be x equal to negative 6 and x equal to 1. Visually, if I wanted to graph this function and show you those vertical asymptotes, I could do this. Let me clear this. This is extra that doesn't need to be done. But I can graph the function 3x minus 18 divided by x squared plus 5x minus 6, doing a zoom standard. The graph's going to have a vertical asymptote at x equals negative 6, which is there, and a vertical asymptote at x equals 1, which is there. If I wanted to graph those on my calculator, I need to take the factor that produced the vertical asymptote, multiply it by 1,000, and put it in a y. So I can, to get the vertical asymptote at x equal negative 6 that I can't see, on my calculator, I can multiply 1,000 times x plus 6. X plus 6 is the factor that gave me the vertical asymptote at x equal negative 6. multiplying that factor by 1,000 gives something on my graph that looks like a vertical asymptote. So there's the one at -6. To get the vertical asymptote at x equal to 1, in my y2, I'm going to type in 1,000 times the factor that made that vertical asymptote of x minus 1. Or into my y3, I guess. This was a y2 and that was a y3. Because I already had the y1 used up. And there's that vertical asymptote. Vertical asymptotes are vertical lines that the graph doesn't touch nor cross, but it gets infinitely close to on either side of that line. So done with 4a, give 3 a go. And let me move on to 5 and 6. For 6a, to find the domain of that fraction, given in number 6, I'm going to ignore the 3x squared plus 20x plus 12. And I'm going to solve the x squared minus 16 equal to 0. I'm going to solve that by factoring. That factors into x plus 4 times x minus 4. Once I have it factored, I'm going to set each of the factors equal to 0 to get the numbers to exclude from the domain. The numbers that I exclude from the domain are x equal to -4 and x equal to 4. For 6a, I'm going to say the domain of the fraction f of x equals 3x squared plus 20x plus 12 over x squared minus 16 is all real numbers except -4 and 4. So that's my answer to 6a. When I go to do 6b, the vertical asymptotes are going to be x equal to -4 and x equal to 4. And I usually abbreviate vertical asymptote VA rather than writing down the word vertical asymptote. So I'll give number 5 a go. And 7 and 8 are a little bit trickier. Let me do 7 just because maybe it's a slightly different trick than number 8. So for 7a, to find the vertical asymptote, I'm going to ignore, to find the domain, I'm going to ignore the x squared minus 16, and I'm going to solve the x cubed minus x squared equal to 0. I'm going to solve that by factoring. There's a common factor of an x squared, so I'm going to factor out an x squared and get x squared minus 1, x squared times x minus 1 equals to 0. Then I'm going to set the x squared equal to 0 and the x minus 1 equal to 0. For the x squared equal to 0, this is really x times x equal to 0. So I can solve that by setting each of the factors equal to 0. So x and x equal to 0. For the x minus 1 equal to 0, I'm going to add 1 to both sides and get x equal to 1. So in my answer to part A, the only numbers to exclude from the domain are 0 and 1. So I'm going to say the domain of the fraction f of x equals x squared minus 16 over x cubed minus x squared is all real numbers except 0 and 1. I don't know if I did this too fastly, but theoretically the only number that when you square it that can be 0 is 0. 0 squared is 0. Any number other than 0, if you square it, you don't get 0. The reason this answer is only 0 is because the only number squared is 0. Another way I could have solved this rather than doing this is I could have did square root plus or minus square root. The square root of x squared is x. The square root of 0 is 0. This would give me x equal positive 0 and x equal to negative 0. X equal to positive 0 is just 0. X equal to negative 0 is really negative 1 times 0, which is 0 as well. So that's maybe said differently, but maybe better for 7a. For 7b, the vertical asymptotes are just going to be the two individual answers that I have here. X equals 0 and x equal to 1. I don't need to write x equal to 0 twice. Alright, so I'll do 10, you can do number 9. For 10a, to find the domain I ignore the numerator of 2. I solve x minus 8 equal to 0, and I get x equal to 8. I'm going to say for 10a, the domain of the fraction f of x equals 2 over x minus 8 is all real numbers except 8. When I go to write my answer for 10b, the vertical asymptote is just going to be x equal to 8. So give 9 a go. I think I have too many of these problems. For 12, for part A, I'm going to ignore, as I'm finding the domain, I ignore the numerator of 3x. I'm going to solve the x squared minus 25 equal to 0. I'm going to solve this by factoring. When I factor this, you get x plus 5 times x minus 5 equals to 0. So that's going to give me x plus 5 and x minus 5 equal to 0. I'll solve each and get the numbers to exclude from my domain and get my equations for my vertical asymptotes. The answer for 12a, I can say the domain of the function f of x equals 3x over x squared minus 25 is all real numbers except plus or minus 5. Notice I haven't been writing the x equals because that's kind of implied. For 12b, my vertical asymptotes are going to be x equal to negative 5 and x equal to 5, just the answers to the algebra for part A. Coming up on a video break, and I get some tricky problems. For 14a, to find its domain, I'm going to ignore the 3x minus 12. I'm going to solve x squared plus 25 equal to 0. This is prime. This is a sum of squares, so it doesn't factor. So to solve this, I'm going to minus 25 from both sides. So if you would have written down anything that was factored, what you've written down would have been wrong. That doesn't factor. It doesn't equal x plus 5 times x plus 5. So if you tried to factor x squared plus 25, and you wrote x plus 5 squared, or if you wrote x plus 5 times x plus 5, those are completely wrong. That thing doesn't factor, it's prime. I don't want to get into a whole factoring lecture here. Just know that that's prime. I can sit down with you or point you to a spot in my intermediate algebra lectures in chapter 1 that tell you why that's prime. Anyway, so to solve this, I have to get the x's on one side, the numbers on the other, and solve by square rooting plus or minus square rooting. Square root of x squared is just x. The square root of negative 25 is 5i. So when I solve this, I get x equals plus or minus 5i. Because the numbers that I'm excluding from the domain have i's in them, and my domain is all real numbers except real numbers that I'm throwing out, I'm going to say the domain is all real numbers. So for problem 14a, I'm going to say the domain of our fraction is all real numbers. And the real reason I'm writing real, because when I'm graphing, I don't graph with i's. This one. So I just had a break here in the video. So my domain is all real numbers without an except. You could say except x equal positive and negative 5i, and that wouldn't be wrong, but it's kind of contradicting the domain is all real numbers, and then putting except imaginary numbers wouldn't make sense. So for 14b, since there's no numbers I'm excluding from the domain that are real numbers, the graph won't have any vertical asymptotes. I guess it wouldn't be wrong to say there's a vertical asymptote at positive and negative 5i, but it won't show up on the graph because our graphs don't have i's on them. If I graph this function by clearing out all the stuff I have in there. And do a zoom standard. The graph that I have won't have any asymptotes. In fact, it's so close to the x-axis I can't see it. Let me really crunch my window of my y's down, maybe like to -1 to 1. Now if I look at the graph, it doesn't have any vertical asymptotes. It goes as a continuous unbroken graph. You're only going to get breaks in the graphs of fractions if there's values of x that make the denominator equal to 0. Since there aren't any values of x that make the denominator equal to 0, there's no vertical asymptotes. Oh, give 13 a go. It should be very similar. Similarly, 15 and 16 should be very similar. For 16, part A, to find the domain, I'm going to ignore the numerator of 2x. I'm going to solve the x squared plus 1 equal to 0. That doesn't factor. It's a sum of squares, which is prime. So to solve this, I'm going to -1 from both sides and get x squared equals to -1. And then I'm going to go square root plus or minus square root. I'll get x equals plus or minus I. That's an imaginary number. I don't really need to exclude that from my domain. When the numbers to exclude from the domain are imaginary numbers, when we go to write the answer, we say the domain is all real numbers and we don't include the except part. So the domain of the function f of x equals 2x over x squared plus 1 is all real numbers. Just like the last graph, this graph's not going to have any breaks or vertical asymptotes in it. When I go to answer part B, I'm going to say there's no vertical asymptotes because the numbers I and -I don't show up on a regular graph of real numbers. So give 15 a go. And we're done with the first kind of problems. We'll move on to the second kind of problems, which will finish up this video. They want me to find x and y-intercepts of graphs. Real easy to do. We've already found intercepts earlier this semester. To find x-intercepts, so for 18a, if I want to find an x-intercept, I just set the function equal to 0. So the function is 3x minus 12 over 2x plus 6. To find the x-intercept, I set my function equal to 0. I'm going to rewrite that 0 as a fraction so I can cross multiply. And then I'm going to cross multiply up and cross multiply down. And I'm going to get 1 times 3x minus 12 equals 0 times 2x plus 6. On the left-hand side, I'm going to get 3x minus 12 because 1 times anything is itself. On the right-hand side, I get 0 because 0 times anything is 0. Now I'm going to add 12 and divide by 3. Get 3x equal to 12. And then divide by 3, and get x equal to 4. So my answer for the x-intercept, it has to be written as a point. And as a point, the opposite letter is always 0 for an intercept. The opposite letter of an x-intercept is a y, so the y needed to be 0. Done with part A, I'll move on to part B. To find the y-intercept, you plug 0 in for the x's. So I'm going to go f of 0 equals 3 times 0 minus 12 over 2 times 0 plus 6. The pieces with the zeros turn into zeros. So this really simplifies to f of 0 equals to minus 12 over 6, which is minus 2. When I go to write my answer for the y-intercept, the opposite letter is always 0. The opposite letter of y is x, so the x is 0. So my answer to part B, the y-intercept is the point 0, negative 2. The x-intercept is the point 4, 0 for part A. So you should be able to do 17. I'll move on and do 19 and 20. Eventually I'm going to get slick on the x-intercepts. So for 20a, to find the x-intercept, you take the whole function and set it equal to 0. So I'm going to go 3x minus 18 over x squared plus 5x minus 6 equals to 0. I'm going to write that 0 as a fraction so I can cross multiply. and I'm going to cross multiply up and cross multiply down. Cross multiplying down, I get 1 times 3x minus 18. Cross multiplying up, you get 0 times x squared plus 5x minus 6. The left side, 1 times anything is itself. The right side, anything times 0 is 0. So I get 3x minus 18 equals to 0. Now I'm going to plus 18 and get 3x equal to 18, and then divide by 3 and get x equal to 6. As I go to do an answer for part A, the x-intercept, the opposite letter is always 0. The x is 6, so the y is 0. Hopefully you're starting to notice something in the algebra for the x-intercept that makes you think there's a shortcut, because there is a shortcut. For 20b, to find the y-intercept, I plug in 0 for x. I go f of 0 equals 3 times 0 minus 18 over 0 squared plus 5 times 0 minus 6. All the pieces with zeros turn into zeros, so this simplifies to f of 0 equals minus 18 over minus 6. That comes out to be positive 3. When I go to write my answer for 20b, the opposite letter is always 0. The opposite letter of y is x, so the x is 0 and the y is 3. Real quickly, look at the algebra for my x-intercept. The algebra for my x-intercept ultimately came down to solving 3x minus 18 equal to 0. That's not a coincidence that the algebra ultimately came down to setting the numerator equal to 0. In problem 20, the algebra wound up having the numerator equal to 0 at some point. In problem 18, the algebra that I did to find the x-intercept ultimately came down to setting the numerator equal to 0. That's the shortcut. To find an x-intercept of a fraction, you don't have to do this junk for cross multiplying. The shortcut is to ignore the denominator and set the numerator equal to 0. The cross multiplying will always work, but it will always take you to the same path. So the shortcut to find the x-intercept of a fraction, rather than setting it equal to 0 and cross multiplying, is to ignore the denominator and solve the numerator equal to 0. If you don't like that shortcut, you can do exactly what I did for problems 20 and 18, meaning set the fraction equal to 0 when you find the x-intercept, rewrite the 0 as a fraction, 0 over 1, and cross multiply. The cross multiplying part by the 0 always gives you 0 times the denominator, and 0 times the denominator is going to be 0. That's why I don't really need to do this, because this piece is always going to turn into 0. So when I go to do 22a, to find the x-intercept of this fraction, I'm going to ignore the denominator, and I'm going to set the numerator equal to 0. And I need to solve this by factoring, so I'm going to do bottoms-up factoring. First step I'm going to do in my factoring is I'm going to multiply by 3 and rewrite. That's going to give me x squared plus 20x plus 36. Then I'm going to factor. This is a double plus. The last have to multiply to 36 and add to 20. That's going to be 18 and 2. And then I'm going to divide by 3, reduce, and bottoms up. So x plus 18, I'll divide it by 3. X plus 2, I'll divide it by 3. The first fraction comes in to be x plus 6 when it reduces. Second fraction turns into 3x plus 2 because I bottoms up. So when I go to find this x-intercept, I needed to factor this. I factored it and got x plus 6 times 3x plus 2 equal to 0. Now I can find my x-intercepts by splitting the factors up and setting each one equal to 0. So I'm going to set x plus 6 equal to 0 and 3x plus 2 equal to 0. The x plus 6 equal to 0 gives me x equal to negative 6. The 3x plus 2 equal to 0, I'd first minus 2 from both sides and get 3x equal to negative 2, and then I'll divide by 3 and get x equal to negative 2/3. The answer for my x-intercepts are going to be the points negative 6, 0, and 2/3, 0. Let me just write the answer down here. So for 22a, my x-intercepts are going to be negative 6, 0, and negative 2/3, 0. For part B, to find the y-intercepts, there's no trick. I just plug in 0 for x. I'm going to get f of 0 equals 3 times 0 squared plus 20 times 0 plus 12 over 0 squared minus 16. All the pieces with zeros go away, and you're going to be left with f of 0 equals 12 over minus 16. And I can reduce this by hand, or I can use my calculator and go 12 divided by minus 16. Math, enter, enter. My calculator tells me this reduces to 3/4, and my calculator likes the negative in the numerator, as do I. So that comes out to negative 3/4, and my answer for my y-intercept is going to be the point 0, negative 3/4, because the opposite letter is always 0, and the y-intercept, the x, is going to be 0. So give 21 a go. It's more bottoms-up factoring. For 24a, to find the x-intercept, the shortcut is just to take the numerator equal to 0 and ignore the denominator, so you don't have to do that cross-multiplying if you don't want to. So I'm going to do the shortcut, and I'll set the numerator equal to 0. I'm going to add 18 to both sides, which will give me 3x equals to 18, and then I'll divide both sides by 3. That will give me x equal to 6. For an answer to 24a, write it as a point with the opposite letter 0, so I'm going to write the point 6, 0. For 24b, to find the y-intercept, I'm going to plug 0 in for x, so I'm going to get 3 times 0 minus 18 over 0 cubed plus 5 times 0 squared minus 6 times 0. All the pieces with the zeros turn into zeros. So this technically turns into 0 minus 18 over 0 plus 0 minus 0, because each piece with a 0 turns into a 0, which actually turns into minus 8 over 0, which doesn't equal 0. Minus 8 over 0, if I do it on my calculator, I get some divide by 0 message. Dividing by 0 is undefined. Because this right here is undefined, there's going to be no y-intercept. The graph is not going to cross the y-axis. So my answer to part B for the y-intercept, the algebra that I did to find the y-intercept gave me a fraction that was undefined. When the fraction is undefined when you're going to find an intercept, the graph doesn't have one of those intercepts. Just like when you're going to find an x-intercept, if you get an I, the graph does. When you're going to find a vertical asymptote, if the algebra has an I, the graph doesn't have vertical asymptotes. If you're going to find an intercept and the algebra gives you an undefined, the graph doesn't have that intercept. So your 23 should have the same trick for the, at least for the y-intercept. I made a mistake when I tried to find the x-intercept, so I'm cutting it out. For 30, part A, when I go to find the x-intercept, it's enough just to set the numerator equal to 0. So I'm going to set the numerator equal to 0 and solve for x by adding 12 to both sides to give me 3x equals to 12. And then I'll divide both sides by 3 and get x equal to 4. So the x-intercept is going to be the point 4, 0. When I go to do part B, the y-intercept, I'm going to plug in 0 for x. I'm going to go f of 0 equals 3 times 0 minus 12 over 0 squared plus 25. The pieces with the zeros go away, and I get minus 12 over 25, which is a fraction that doesn't reduce. So the y-intercept is going to be the point 0 minus 12 over 25. So give 29 a go. We have one more problem for this part of the video, and then we can be done with this part of the video. So there could be a hiccup in the video. I made a mistake when I did problems 31 and 32, and I was doing problem 31 when I made the mistake, so let me do 31 instead of 32, and this is going to finish up this video. So to find the x-intercept, I can either set the whole fraction equal to 0 and cross multiply, or I can just set the numerator equal to 0. So as I go to do 31a, you can take the entire fraction, 5x over x squared plus 9, and set it equal to 0. If you do it that way, then you do 5x over x squared plus 9, write the 0 as 0 over 1, and then you'd cross multiply. It could be new colors happening here because I'm in a new day. When I cross multiply down, I get 5x times 1. When I cross multiply up, I get 0 times x squared plus 9. That's going to give me 5x on the left side equals 0 on the right side. I'm going to divide both sides by 5. On the left side, the 5's will cancel, leave me with an x, and on the right side I get a fraction with a 0 in the numerator. When I go to write my answer to problem 31a, the opposite letter is always 0, so for my x-intercept, I'm just going to write it as the point 0, 0. The better way to do the x-intercept would have just been to take the numerator, 5x, and set it equal to 0. And I could have found the x-intercept way quicker, and this is what you should be doing. Finding the x-intercept of a fraction, you can set the whole fraction equal to 0 and cross multiply, or you could just set the numerator equal to 0. To save myself that quantity of work, if I just would have taken the numerator, set it equal to 0, divided both sides by 5, I still would have gotten the same x-intercept. For 31b, to do the y-intercept, I'm plugging in zeros for x's. So I'm going to go f of 0, changing that x to 0, equals 5 times 0 over 0 squared plus 9. That's just plugging in zeros for each of the x's. And when I do this, 5 times 0 in the numerator is 0. In the denominator, the piece with 0 kind of goes away. It leaves me with a 9. I'm left with a fraction with a 0 in the numerator, and fractions with 0 in the numerator equal to 0. My answer to 31b is going to be the y-intercept. The opposite letter is always 0. The opposite letter of y is x, so the x is going to be 0, and the y part is that 0 as well, but the 0 is from the answer. So the y-intercept is going to be 0, 0. So that should be a good breaking point for this section. We'll move into a part 2 here in a bit.